Hello everyone. Hope you are good in health. We are discussing the modern periodic table. Let us talk about hydrogen. There is an anomaly when it comes to the position of hydrogen. What is the meaning of anomaly? It is exception. Okay, so there is an exception when it comes to position of hydrogen because it can be placed either in group 1 or group 7. Can you say why is it so? It can be placed in both the groups. The reason is hydrogen has one electron in first orbit, and that is its outermost orbit. So, in group number 1, all the other elements have similar property that they have one electron in outermost orbit. Here, hydrogen also has one electron in outermost orbit. So, like these other metals, hydrogen will also lose one electron and can form compound. So that is the reason that it can be placed in first group. Another reason that it can be placed in group 17 also. Now we know group number 17, that is halogens, and all the elements in group 17 gain electron. Here, while forming compounds with hydrogen, it can gain electron also, okay, to fill its configuration. That is why it can be placed in group number 17 also. So these are the reason for position of hydrogen, that it can be placed in group 1 also or in group 17 also. Now let us talk about the elements present in second period. First element of second period is lithium. Now again, I want you to look at its electronic configuration. In first orbit, 2 electrons. In second orbit, 1 electron. What is outermost electrons for lithium? 1. 1 valence electron for lithium. The next is beryllium. It has how many electrons as valence electrons? 2, right? In first orbit already 2 are there, in second orbit again 2 are there. So 2 are valence electron for beryllium. The next we have is boron. How many valence electrons are there for boron? 3. Okay. Then we have carbon. Electronic configuration of carbon is 2, 4, which means 4 electrons are valence electrons. Then we have nitrogen, 2, 5. How many are valence electron for nitrogen? 5. Then we have oxygen, 2, 6. 6 valence electrons for oxygen. Fluorine, 2, 7. 7 electrons are valence electrons. Then we have neon, 2, 8, which means there are 8 valence electrons for neon. What did you observe for all these elements present in period number 2? Do they have same number of valence electron? No, right? Lithium has 1, beryllium has 2, boron has 3, carbon has 4, and like that. Which means we do not have same number of valence electron in one period. Whereas recall, we learned that in one group all the elements have same number of valence electrons, whereas in period they do not have same number of valence electrons. What about shells? Do this element contain same number of shells? Yes, they contain same number of shells. If you see, lithium has also two shells, Kl. Beryllium also has two. Boron has also two. Same way, all these elements present in this period number 2 have same number of shells. So here we got another property, that the elements present in same period do not have same number of valence electrons, but they have same number of shells. Please remember this property. We can also say that the atoms of different elements with same number of occupied shells are placed in the same period. Okay, different elements with different valence electrons but with same number of shells are placed in one period. Let us take another example. We'll look at period number 3. The elements present are sodium. Sodium has electronic configuration 281. Here you will see that 1 is valence electron and 3 shells are there. Magnesium has 2 valence electrons. How many shells? 3 shells. Aluminium, 3 valence electrons, and how many shells are present? 3. Silicon, 284, 4 valence electrons and 3 shells. So this way, other elements also, phosphorus, 5 valence electrons but remaining 3 shells only. Sulfur, 6 valence electrons, then also 3 shells. Chlorine, 7 valence electrons and 3 shells. So here, by taking example of period number 3 also, we can see that the elements present in same period will have different number of valence electrons. Valence electrons will not be same, but what will be same? Number of shells. As we can see, for period 3, 3 shells are present. Okay, so I am sure by these two examples it is clear to you. How can we explain the number of electrons present in different shells? Till now we have learnt the names of shells, right? K, L, M, N. First shell, that is K, second is L, third is M, and fourth is N, like this. How can we remember and how can we decide that this many electrons will be there in first shell, second shell? So that maximum number of electrons can be filled in a shell depends on the formula 2n square. This formula you need to remember. This is formula for what? It is formula to decide the maximum number of electrons can be filled or can be accommodated in a shell. Okay, so 2n square is the formula. Let us see the table and find K. Okay, first shell. K is first shell. N represent number of shell. So here n is equal to 1. Okay. Now formula is what? 2n square. So 2 multiplied with 1 square. 1 square is what? 1 multiplied with 2 is equal to 2. This means it is concluded that in the first orbit maximum 2 electrons can be filled. If we talk about L shell, L means second orbit, which means number of orbit n is what? 2. If we put this value in the formula 2n square, we will get 2 into 2 square. 2 square is 4, 2s are 8. So in second orbit, maximum 8 electrons can be filled. So this formula you will remember, it is 2n square. What formula it is? The maximum number of electrons that can be accommodated. Now in third orbit, 8 electrons can be filled. In fourth orbit, 18 electrons. in fifth 18, in sixth 32, and in seventh again 32. Okay, so it will be like 2, 8, 8, 18, 18, 32, 32. Now you will be thinking, why is it so? The reason for this you will study in your higher classes. Here just you will remember the formula 2n square. Okay. Now, the position of an element in the periodic table tells us about its chemical reactivity. How will it react with the elements? So, let us now learn one by one.